Hi everyone. So I'm back after a break on the series, and in this video we'll look at the pumping lemma. The first question is, what is the pumping lemma? So the pumping lemma is what we can use to show that a language is not regular. So we'll look at the statement of the pumping lemma in just a bit, but there's one thing that I um, want you to keep in mind, which is that the pumping lemma can be used to show that a language is not regular, but it cannot be used as a proof of regularity. So I'll just put it in the corner here. This is something that you really need to keep in mind, that regular implies that it satisfies the pumping lemma, but just because something satisfies the pumping lemma does not mean that that language is regular. So this is something that we need to keep in mind. And now let's look at the statement of the pumping lemma, and my aim in this video is to just simplify the statement of the pumping lemma, and we look at a more generic algorithm in the next video which we can use to prove that any language is not regular. So this is the statement. If L is regular, it has a pumping length P where all strings S such that the length of S is greater than or equal to P can be divided into three parts X, Y and Z such that all of the following conditions are satisfied. So let's look at the conditions now. The first condition is that x, y to the power I and z should belong to L for all I. The second condition is that the length of y should be greater than 0. And the third condition is that the length of x and y together should be less than or equal to p. The third condition is not extremely important, but it makes the pumping lemma stronger. So what the pumping lemma is saying essentially is that in any regular language I can find some substring in the middle, and I can have any number of concatenations of that, so I can expand that substring in the middle itself as many times as I want, and my string will still belong to L. And at this point, mostly the languages that we talk about are infinite languages. So we're not very worried about finite languages because we know that those are obviously regular. So by infinite languages, I mean languages with infinite number of strings. So what the pumping lemma is saying, let's look at it from with an example that makes it much simpler. So we can look at the example, which is all strings ending with 0, our very popular example, and we know that this is regular. Remember, how do I show a language to be regular? I either just write the regular expression for it, or I just make an automaton, a finite automaton for it, and that proves that the language is regular. So for all strings ending with 0, all I have to do is say 0 plus 1 star and then a 0. And of course my alphabet is 0 and 1. So this here is my language. Now what the pumping lemma says is I'll have a pumping length. So let P be my pumping length, which is, let's say, 3. So I can take any language which is greater than or equal to 3 in length. So any string which has at least 3 symbols or more. So let's take an example which is, let's say, 0 1 0 0 1 0. And now what happens is I'm saying that there will always be some substring in the middle which I can have any number of concatenations of. So let's say my x is this thing right here, my y is this thing right here, and z is this. So this is probably not the greatest example because x and y together are not less than or equal to p in length. So we might want to change our example, but we could leave it as it is as well. So what we do now is we are saying that we can have x, y to the power I and z for any I, and what we are claiming is that this thing will still belong to our language at the top here. So let's take I is equal to 2, let's say. So what happens here is I write y twice, so I write 1 0 1 0 0 1 and 1 0 0 1 again, and then a 0. So this is one y and this is another y, so that gives me x y squared z. And as you can see, this still belongs to the language at the top, which is all strings ending with 0. So that's what the pumping lemma says, that for any regular language I can always find some pumping length, and then I can always find some substring in the middle, of which I can have as many repetitions in the middle itself. So we can now look at a language which is not regular. So let's say I take the language a to the power n, b to the power n, are very common example of a non-regular language. Now what happens here is, let's just say my p is some random number, let's just say 3 again. Now what's going to happen is, when I take a string of length greater than 3, let's just say I take a string of length 4, which is AABB. Now I can have 3 conditions. One of them is I can take y to be in the A part, I can take y to be in the B part, or I could take y to be as A and B, some part of A, some part of B. So let's take an example. So let's say this is my x, this is my y, and this is my z. Now what happens is, when I do x y to the power 2z, what happens is I have a, and then I have this is one y, this is another y, and then I have two b's, which is z. Now here I have 3 a's and 2 b's, which means that it does not belong to the language that I have here. And similarly, when I take y in the b part, my b's are going to be more and a's are going to be less, so that won't work either. So when I take something like this, maybe the third condition is I can have y to be AB, so this is y, and this is x, this is z. So now what happens is, when I take x y squared z, what happens is I put x once, which is 1a, then I need to put y twice, so I put y once, that's y once, that's y the second time, and then the z, which is a single b. So this is my y and then y again. Now this string right here has completely broken the pattern itself, so this definitely does not belong to our language. So that's what the pumping lemma is saying, that because this language is not regular, we are never going to be able to find a substring in the middle such that we can have as many concatenations or as many instances of that substring in the middle while still keeping our string in the language. So that's a brief overview of the pumping lemma. What we'll do in the next video is we'll look at how we can actually use the pumping lemma to prove that any language is not regular, and we'll see a more generic method that we can use. So that'll be for the next video. Guys, if you like the video, please do give it the thumbs up and subscribe to my channel if you haven't already, and share the video with your friends so that they can learn as well. I'll see you next time.